Okay, welcome to this recording basically for problems on chapter 37. Okay, I have listed in here basically these problems from chapter 37: 51, 52, 63, 66, 68. Problem 70, I'm not going to do it here because I already provided the solution on Canvas. I'd like you guys to look at that solution. I know I did not use a notation that is commonly used when we get into relativity, namely usually we use the that is actually to reduce the size of the writing, that's all. Basically, instead of taking the partial with respect of any variable, let's say for example with respect to x, the notation, the common notation is they use the partial x basically to indicate that if I've used it, the 2.5 pages or so would be a lot less than that to make, because there are a lot of derivatives in that. So basically what the problem 70 was, it gave us the wave equation. Let me write the wave equation quickly in here. And the wave equation basically that's for the solution for, or at least the last equation for the electric field inside based on Maxwell's equations basically in free space. So this is basically the equation you end up with if you do that problem, namely that there are no currents and no electric no charges basically in free space. So if you do that, basically you will find that the one of the components of the electric field would behave this way at least, and another component for at least the magnetic field would behave in similar fashion, and the wave, I took it in this simplified version in here, at least the problem did, traveling in the x direction. So basically this is the based on Maxwell's equation. Well, the problem states basically if we were to use classical mechanics, let's say for example you are on a train and you want to measure positions relative to you in the train. If I give you the coordinates in space outside in the station, for example, this is a transformation you use. This is Galilean transformation from classical mechanics. Time is absolute in classical mechanics. So the point is, if you do the substitution and do the change of variables in here, the equation does not reduce to a wave equation as is. The equation is not invariant, actually changes. So that's one thing. First, what that means, basically what that means is that it's no longer a wave, it's something else. And that's a problem because if you can do this experiment, basically if it's true, then you could ride on a train, shine a light, basically that's what the EM waves are, and then they will stop behaving as waves, and that's not what is what we see, at least according to experiment. That's one problem. The other problem actually also, it seems like the velocity will, and when you do that, becomes one of the properties of the new equation, and that's a disaster because then that means that that experiment will tell me which thing is moving. Is it the train or is it the station? And then I can definitely tell that there is a preferential preferred, if you wish, inertial frame, and that violates, of course, even classical relativity based on Galileo transformations. So that's basically what the first part of the problem is. The second part of the problem is says that if you use, so this is the old Galilean transformations, but if you use Lorentz transformations basically under the conditions of the postulates of Einstein, you will find that these are the transformations, by the way, where gamma is a factor that is 1 over square root of minus beta squared, and beta is basically the relative speed with respect to time. And also time is not universal. Time actually changes from frame to frame depending on the factor gamma, and this is how time changes. So basically minus v over c squared times t, times x, I'm sorry. So that's basically how I'm going to transcribe that. If I use these transformations, what happened was this equation retains its form, okay, with respect to the new variable squared, of course, sorry, minus 1 over c squared, the partial derivative of the electric field now with respect to the transformed value of that electric field. I made a fuss in the derivation there, hopefully you guys will have time to go through it, that the entire factor that comes before this was a gamma squared, and that's true, okay? So for this particular case, it cancels and you have no problem whatsoever. You ask, well, what happened, for example, and it didn't make that point in there, what happened if I have a forced oscillations, if I have a wave that is, for example, driven by some sort of external factor in here? So, of course, the second half will not be zero, and this solution with a zero, and it will be just a transient behavior. So I ask, what happened to the steady state? Isn't that going to pick up another factor of velocity? Because there was actually a term in here. First of all, I mean, before I do that, this term gamma squared will not be cancelled because there will be no zero on the other case for the other side, basically, when there is transient. So there is a problem there. But what I basically did not mention, and I think you guys, hopefully you saw it already, is that there is a factor in here that appears naturally in the expression also. Okay? So even if the zero is not there, there should not be a problem, because actually this is exactly 1 over gamma squared. And that will cancel this gamma squared, and all is right. Everything is good. So hopefully you guys will have a chance to go through that problem. Usually this typical problem is actually an extension of the lecture, because the whole point in here is that classical mechanics is not compatible with Maxwell's equations, and that's really one of the reasons why Mr. Einstein starts to think that there is something the matter with it, and that's how basically he arrived at his theory of relativity. So and that's even before he knew about Michelson and Morley experiment about the constants of the speed of light. Okay, he was making case for that, and at the end, of course, it was obvious later on. And although the experiments for Michelson and Morley were done way before he actually put this theory out there. So, problem 51. Problem 51 is about the Cherenkov radiation. Cherenkov radiation is basically similar to the Doppler effect. Yeah, similar to the Doppler effect, except for light, basically. The sonic boom, basically, except for light. So basically what you have is the following. You have a medium in here. For the case of this problem, it's a glass with an index of refraction n equals to 1.52. That means that light in here would be traveling less than the light in vacuum, which is given by this expression that we saw in optics. So basically, this is the speed of light there. Obviously, because n, the index of reaction, is always greater than 1, that means the speed of light in any medium is less than that of the speed of light in vacuum. So, and the postulate from the relativity is about the speed of light in vacuum being the ceiling. So this one is not. So if, for example, a particle, and this is an interesting problem because when I visited with my students when we were in different college, basically we went to a nuclear reactor, we saw the Cherenkov effect actually with our own eyes. We're not allowed to take cameras with us into the reactor, but that's basically what the beauty of that is. You can Google it and you can see a lot of those blue lights. Basically what happened then is you have so-called positrons, which are charged particles, electron charged positively. Or actually, is it electrons? Yeah, I think they are charged particles that come in here from the nuclear reactor. Actually, they come in from the rods themselves super fast. Okay, they emerge from this one super fast, and they're moving faster than this speed, in the speed of light in this medium. Okay, they're still below c, but they're greater than this value. Okay, so imagine if c is 300,000, actually 300,000 kilometers per second, you divide it by 1.5, so it's going to be about 200 and something thousand kilometers per second, and these ones are emerging with speeds that are super high compared to this value, higher than this value, but still less than c. So this is basically the Cherenkov radiation, and that's basically what the problem is talking about. Cherenkov at the end won Nobel Prize for it. So the problem in here is asking you, what is the minimum kinetic energy in electron volts that an electron must have while traveling inside the slab of crown glass n equals to 1.52 in order to create the Cherenkov radiation. Okay, for it to create the Cherenkov radiation, at least its velocity must be greater than or equal to this speed. Okay, now the factor beta then must be equal to, remember, v over c, so it must be equal to 1 over n. Okay, clearly. Okay, so that's basically how much it is, and 1 over n is less than 1, of course, because n is always greater than 1. So that's good. So gamma in this case is going to be equal to 1 over the square root of 1 minus 1 over n squared. You can work this expression to find it being n squared, I'm sorry, n, when you take it from the square root, divided by n squared minus 1. Okay, so this is the factor gamma. From here we can find the kinetic energy. We saw in lecture that the kinetic energy for this particle is going to be simply the mass, and in this case, what type of particle it is? It's an electron. So this is the mass of the electron times the speed of light times the factor gamma minus 1. So basically this entire expression minus 1 times the speed of light. The only exception in here is that we have to divide it by the charge of the electron, because this expression is going to be in joules. And a joule, if I have one electron moving in 1 volt, that is an electron volt. So an electron volt is basically one electron inside of 1 volt, and that will correspond to 1.6 times 10 to the negative 19 basically joules. Okay, so that's part of the conversion that we need to do. So in other words, just divide this by E, and you're going to find an expression in here that is going to give you, let me set the value of gamma. Actually, I should really find the value of gamma. Usually we really have to find it to find exactly what these things are. So let me put it quickly in the calculator. You know what? Let me leave it to you guys to do it, okay? Let's you guys have finished that. I know there are a few questions before, so hopefully you picked up on them. And this, I think this is the third question in here for the discussion, so hopefully you pick up this one too. And that is to finish the algebra in here, to finish the basically the calculations in here. So I have gamma, which is given by n, or if you like, 1 over square root of 1 minus 1 over n squared, and n is given 1.52. The mass of the electron is 9 times 10 to the negative 31 kilogram. C, I'm going to take it to be just, so this is ME. C is going to be, how much is it C? Usually it's 3 times 10 to the power 8 meter per second. And the charge of the electron, I'm going to take it to be 1.6 times 10 to the negative 19 coulomb. And if I do that, this kinetic energy is going to be exactly in electron volts. You will find that the number is huge. So usually we express it in terms of mega electron volts. So in other words, don't forget to divide it, the entire expression by a million, and you're going to get it, the expression in mega electron volts. So that's all the question there is to it, and you'll find that there is tremendous amount of energy is needed for this Cherenkov radiation, and that's from a nuclear reactor. That's not something out of the realm of the possibility, because those escaping particles, neutrons, also do that too. They escape at super high velocities in there. Okay. Anyway, so that's question number 51. Question number 52. So the trick in this problem is just to make sure that the speed is equal to at least the speed of light in that medium. Okay. Problem 52. Problem 52 basically gives you a model for the proton, and it says the proton, you can think of it as a combination of three, and we'll see that later on, 3 quarks. You have 2 up quarks and 1 down quark. Okay, and they give you the mass of this up quark and down quark, and you can clearly see from the problem that if you add up 2 of this plus 1 of those, it's a lot less, a huge factor less than the mass of the proton. So there is a big missing mass in here. Where is that mass is going? That's probably with the model, if we're really going to think that there is a 1 in here and 1 in here and all of 3 of them. So basically these 3 quarks, 2 of them of the same kind and another one of a different kind, they form the proton. So if you add up the masses, they don't add up to exactly the mass of the proton, so because they are too tiny. So the question is, estimate, where is it? First of all, suppose we incorrectly, of course there is better models to do this, the rest energy of the proton, so this is the proton at rest, is equal to the is derived from the kinetic energy of 3 quarks, and we split that energy equally among them. So each and every one of these quarks, basically you have 2 that are being of kinetic energy for the up quark and 1 for the down quark, and if you add them together you'll find that this is basically, because the rest mass for each and every one of these ones is so tiny, it's negligible, so all the energy really is that of motion for these particles in there. So that's basically why the assumption is. Furthermore, these 2 energies are equal, so that means 3 the kinetic energy of an up quark must be equal to that of a proton. Furthermore, this quantity, the kinetic energy of a proton from the lecture, if you guys remember, it's the mass of the quark times the speed of light times the factor of gamma minus 1. This must be equal to, of course, MP. Okay, why is the screen went blank? Hopefully the recording is still on. Anyway, so MP times c squared. The c squared of course cancel, and from here we're gonna find the factor gamma equals to 1. I put 1 on the other side already. The ratio of the two masses, of course the factor of 3 in here, mu. So the only thing in here to note is that this ratio is a huge factor. Okay, you have 1.67 times 10 to the negative 27, that's the mass of the proton. The mass of the up quark, don't forget the factor of 3, is just 4.11 or 4.12, I'm sorry, 10 to the negative 30. And if you do the algebra, it's going to be 1670 divided by 3 times 4, which is 12. So it's going to be a few hundred plus 1. Don't forget that 1 in there. Okay. So you're going to find the number for gamma in here. This is for the up quark. Okay. We need to find the gamma for the down quark. It's going to be the same analogy, except that this is the mass, has to be the mass of the down quark. That's all. So the ratio in here, instead of having a 4 in there, it's going to be an 8.59, 8.6 basically, times the same thing in here. So it's going to be slightly less because this factor in the denominator is higher. So this number is going to be less. And we're going to find a different value for gamma. Estimate, so we're going to find the two Lorentz. Similarly, estimate the for the down, so they will answer both A and B. So this question was A, this was B, and then it says, are the corresponding VU and VD greater than 99% of the speed of light? We really have to do this in order to find this number, okay? We really have to do this to find what these numbers are. So let me get the value in here for gamma u. Well, I'm pulling a calculator here on my screen. Okay, gamma u. So I have 1.67 times 10 to the power 3 divided by, okay, divided by 3 times this number. 3 times that number. So it's going to be 135 plus 1, that's 136. So this is roughly 136, okay? How about this guy in here? Now we're going to find the speeds quickly from this expressions in here. Okay, so the mass changes in here. So instead of 4.12, I actually have 8.59. So this is 64.8 plus 1, that's 65. 65. So gamma is very huge for both of them. Okay. Beta, remember, 1 over square root of 1 minus beta squared is the gamma in general. So this will give me an expression, if I invert the expression, 1 over gamma squared is equal to 1 minus beta squared. So 1 minus beta squared is equal to 1 over gamma squared. Move the gamma squared to this side, move the beta squared to the other side, and I'm going to find an expression for beta, which is basically 1 over the square root of 1 minus 1 over gamma squared. Okay, let's find the two numbers in here. So we're going to plug in gamma u and gamma d in here, and we're going to find the two betas. Okay, 1 over square root of, open parentheses, 1 minus 1 over 135 or 136. Okay. Of course. Did I do something wrong with the algebra in here? Oh man, why is it up above in there? Yeah, of course, I forgot to. It's simply, there is no denominator in here. I'm sorry about the algebra in here. That's wrong, okay? Sorry about that. Beta is clearly 1 square root of 1 minus 1 over gamma squared. That's all. Okay, it's not in the numerator. So basically this expression inverted. That's all. I'm sorry about that. .6. So this is a 99.6%. How about the other one? .65. .2%. Okay, so both of them are almost the speed of light. Okay. Are the corresponding speeds VU and VD greater than 99%? Of course, the question is right. Yes, both of them are. More realistically, so that's the question C, actually, we answered it. So we have the numbers now. Question D, more realistically, the quarks are held together by massless gluons which mediate the strong nuclear interaction. Suppose we model the protons as 3 quarks, each with a speed of 0.9 c. 90% basically the speed of light, with the remainder of the proton rest energy supplied by gluons. In this case, estimate the percentage of the proton rest energy associated with the gluons. Okay, so basically here is the scenario. They are saying now we know the speed of this quarks. Okay, so the speed for the quarks is, let me find gamma. In this case it's 1 over 1 square root of 1 minus 0.9 squared. Okay, because it's 90% the speed of light. So I know the factor gamma then is equal to 1 over basically square root of 1 minus 0.9 squared, and the factor gamma, what did I do here? Oh, and then I forgot. What is this symbol in here? Okay, it's 2.3. So gamma is about 2.3, which is a lot less than before. Remember, the smallest value earlier was 65. Okay. So, we want to know how much energy. So basically this is how the story goes. The kinetic energy for the up quark, 2 of those, plus the kinetic energy for the down quark, plus the kinetic energy or the energy for the gluons, whatever that is, okay, equals to the rest mass of the proton. Okay, so this one is equal to 2 times the mass of the up quark times c squared times gamma minus 1, and gamma is 2.3, so this number is exactly 1.3, plus the mass of the down quark times the speed of light times again the same factor gamma minus 1, which is 1.3. This we need to subtract it from the mass of the proton times c squared, and this is going to give me the energy of the gluons, but they don't want the energy of the gluons, they want a percentage, I think. Okay, estimate the percentage of the proton rest mass associated with the gluons. So if I divide this basically by, so it's going to be percentage now, by the mass of the proton times c squared. So the mass of the proton times c squared, cancel the c squared everywhere. That's the reason why we have to do this ratio. And now we have the percentage. So the percentage, how much percent of the energy is just going into the gluons, okay, is equal to the mass of the proton minus 2 times this whole masses. Okay, first of all, I have a factor of 1.3 that's going to come out. That's exactly this number, minus 2.3 minus 1. And then I have the 2 masses of the down up quark and 1 of the down quark divided by the mass of the proton. Obviously, I cannot neglect now these masses because they are going to be a problem for us. Where is this 2 coming from? Sorry about that. This 2 is not there. Okay, so it's going to be a huge number. Okay, even with this assumption that gamma is 90%, even a lot of the energy is going to the quarks, but it's still mainly going to the others. Okay, so I'm gonna do the algebra a little bit easier for me, okay, for my sake, because it's gonna be 1 minus 2 times the mass of the up quark divided by the mass of the proton, because it's much easier to handle it this way, plus the mass of the down quark divided by the mass of the proton, because we already found this numbers times 1.3. That's the gamma. Okay, except I have to multiply that by 2 and so on and so forth. Okay, so did I do the algebra in there or not? No, I did not. So okay, never mind. So we'll do that. So it's going to be 1 minus, open parentheses, we have 2 times the mass of the up quark, which is 4.12, plus the mass of the down quark, which is 8.59, and this one is times 10 to the negative 3, because there is actually 1670 in the denominator. Okay, it's 98.99% basically, okay, if you do the calculation. So this whole thing is 98.99%. Gluons, energy going to the gluons. Do you guys see the argument in here? This is a lot. Most of the energy is not actually in the particles themselves, it is actually going into the gluons. Those are other particles similar to the photons, we'll get into them later on, that are responsible for the strong nuclear forces. So the gluons carry most of the energy in this case. Okay, almost 99% of the energy is there. Of that of the proton is inside the gluons. Okay, so let's continue this discussion. So that's problem 52. Oh no, we still have another question in problem 52. Basically, model a quark as oscillating with an average speed of 90% the speed of light again, across the diameter of a proton 1.77 meters. Estimate the frequency of that motion. Okay, here is the problem. This has nothing to do with this thing in here at all, because gamma in this case is equal to, we calculated it to be 2.3 already, so gamma is big actually. But I'm going to do a classical mechanics, basically saying that this is oscillating back and forth inside the proton. So this quark is moving one way through the diameter, and then coming back, it would have completed a whole cycle, t. So t in this case is the distance traveled divided by the speed. The distance traveled divided by the speed, and the speed in this case is going to be 0.9 c, and we have the distance 1.7. Did I do it backward? I think I did it. Yeah, no, that's correct. So we will find the period, but we're not asking about period, we're asking about the frequency. So the frequency of oscillations is 1 over t, and that is equal to 0.9 c divided by d, and that is 0.9 times 3 times 10 to the power 8 meter per second divided by the distance, and the distance is 1.7 times 10 to the negative, except that the distance traveled is twice, so I need a 2 in here because we go back and forth. Okay, 10 to the negative 15 meters, or a Fermi meter, or femtometer, or whatever the symbol for it, FM. Okay, femtometer. Okay, so from here you can plug in the numbers. What matters in here is that 2 times 1.7 is about 3, and 3 is about 1, so the ratio is about 1, and 0.9 is about 1. So all of this stuff is just 1. So the order of magnitude for this frequency of the order of 10 to the power 23 hertz. This is very high frequency. This is the gamma rays. Again, that's another gamma that comes into it. It has nothing to do with the Lorentz factor. Gamma rays is just like the X-rays, extremely high energetic particles, high energetic electromagnetic radiation. Okay, so that's problem 52. Problem 63. Problem 63 is basically trying to plot. So this is the scenario for problem. Again, we visited with my students in the past the lab in Chicago. What is that lab? Fermi lab. Yeah, Enrico Fermi. I mean, we're mentioning him today too many times. Okay. In that lab, basically, they detect basically neutrinos, and they do all kinds of elementary particles. So this is a scenario with this one, except in this case, what you have a nuclear accelerator or linear accelerator, and you're accelerating particles, and as they move faster and faster, you're detecting their lifetime. Okay. Obviously, usually when there is a smash, when there is a collision, and those atomic smashers, basically what happens is a particle will fly in all of the directions, and you take a picture of them, and you will see which one were moving fast and how long they survive, and based on their electrical properties and things like that, you identify them, and you identify, among other things, their lifetime before they decay. So here is one. You have the data in here. Your classmates or your partner suggested that you plot delta t squared, so this is the time, okay, as a function of 1 over 1 minus beta squared. Okay, no, the whole thing is squared actually, so gamma squared, basically that's the factor that you have in there, gamma squared, which is 1 over 1 minus beta squared. Remember, gamma has square root. Now we square it, the square root is gone. So you're argued why is that best fit, because you're going to find a line in here, so you're going to start somehow the smallest speeds that will correspond to gamma equal to 1, and that's going to be closer to the natural lifetime basically at rest, so it's going to be a line of some sort, okay, the data. And the reason why it is because you know that from the lecture that this time transforms from the rest frame where the particle is not moving divided by the square root of 1 minus beta squared. Okay, so if you square everything, is going to be a line, and now what you're changing is you're changing beta, and doing so you're changing gamma. Okay, so this is basically how gamma squared, so you're plotting delta t squared as a factor of gamma squared, and the slope here will be exactly tau squared. Okay, so the slope is going to be tau squared. And that is the actual life of these particles. I mean, it's amazing. You go under these labs, for example, in the Fermi lab, and you will have particles that you know that they cannot survive their entry. They're cosmic particles. They come from the cosmos, and then they somehow create particles in their collision with the upper atmosphere, and those particles are supposed to only survive for so much. Yet they survived. I mean, they're not supposed to travel, and that's the muon actually. They cannot travel more than 600 meters on their own in their rest frame without disintegrating, but they travel kilometers, about 10-12 kilometers from the upper atmosphere down to the earth, and they survive. So the only way they survive, if from our vantage point, is that their life, they must have existed for a long time, much longer than their own lifetime, their proper lifetime. But for them, the distance of 10, 12, 15 kilometers, this is an interesting problem that we can do later on, is that it should look shortened to be less than 600 meters. So as far as they're concerned, the time did not change. They lived only for that many microseconds, but the distance is shortened. And again, the length contraction as far as they're concerned, because they believe the lab is rushing to meet them, so they're stationary. And from our vantage points, it's time dilation, because we see they lived a lot longer because the distance did not contract. We're living in the lab, so we know the lab did not shrink. But we see them with an extended life. So this is exactly similar to that situation. So we have different values of u over c, and we plot them, and we're going to find this value. And the particle seems to live longer and longer with higher and higher speeds. And that's basically the situation in here. Obviously, I will leave it to you guys to plot this data. You have 1, 2, 3, 4, 5, 6, 7 points of data. But don't forget to square the times. They're given in 10 to the negative 8. So when you square them, it's going to be 10 to the negative 16 squared. And then don't forget to calculate the value of gamma squared, not even gamma itself. It starts with smaller values and it increases all the way to 0.94. Beta, that is, that's the highest value. And you're going to plot it and find. So in here, the question is, use the best fit line to calculate the mean lifetime particle in its rest frame. So basically that's find the slope. Don't forget to take the square root of the slope. Square root of the slope, because the slope by itself is going to be tau squared. So you need to find tau itself, which is square root of the slope. What is the speed of the particle relative to the lab equipment expressed in U over C if the lifetime that you measure is 4 times its rest frame? Question B has nothing to do with the data above. You can solve it in general. So delta T is 4 tau, and 4 tau is, so basically when it's 4 times tau, so it's going to be square root of 1 minus beta squared. Cancel the tau. Doesn't matter which particle that is. Okay? You're going to find the value for beta by, again, going back to that same equation earlier. Beta is just square root of 1 minus 1 over gamma squared. And in this case, square root of 1 minus 1 over 16. Okay? So, because gamma is given to be 4 in this situation. That's exactly what that 4 times is. Okay? Is this the question? What is the speed of the particle relative to your lab equipment if the lifetime that you measure is 4 times its rest line? So it's 4 tau is basically the 4 much, delta T is 4 much tau, and the delta T is given by tau over squared. So basically you're supposed to find that equation, so it's going to be what? Square root of 1 minus 1 over 16, because 4 squared is 16. So it's 96.8%. 96.8%. Okay, almost 97%. So it doesn't take much to reach. So basically, if the speed is very close from the speed of light for these particles, which is the case when they get a lot of energy, so it could live 4 times its own life. Okay, and that's a long time for it to travel that much distance. Okay, let's do problem. Now I think this is the last question. Okay, so part B has nothing to do with the data. You could have done that independently, and sure enough, it's true all the time. This is true no matter what situation is. Even the twin paradox. Okay, you can find how fast one of the twins need to move in order for the other twin to age 4 times as the first one. Okay, how is that possible? So if the first one leaves at the age of 10, and then the other one comes, for example, when the one is 15, the other one will be 60 years old, the one who stays on Earth. That's the equation for it. That's how much speed they need to go, about 97% the speed of light. Anyway, you are an astronomer investigating 4 astronomical sources of infrared data. You have identified the nature of each source, so you know, that's problem 66 I'm looking at, the frequency f0 of when each of them is at rest. Your detector, which is at rest relative to the Earth method, the frequency is f of the moving source. Your results are given. So basically this is a Doppler effect. This is the problem. You're given 4 sources. Think of them of galaxies, faraway galaxies, okay, moving super fast, A, B, C, and then D. Okay, 4 astronomical objects. You're given f in here, you're given f0 in here. All of these frequencies are in terahertz. Okay, what's the tera? It doesn't matter because it's super high. Okay, but 10 to the power 12. Okay, so the first one, it's supposed to be 9.2, whereas it's 7.1. We know from here that it's moving away from us because its frequency as measured in the laboratory compared to what it's supposed to be is less. Okay, since it's less, it's receding, it's not coming towards us. The second one is 8.6, whereas we measure it, that's according to the spectrum line, is 8.6, but when we measure it in the lab, we find it to be shifted toward the red, actually, toward lower frequencies. That means also it's moving away from us. 7.9 terahertz is actually, when we measure it in the line for the spectral line, 7.9, but when we actually measure this specific object, it's shifted towards lower frequencies. This one too is moving away from us. And the last one is 8.9, supposed to be, but we get instead 8.1. All of these objects are receding from us. Okay, which source is moving at the highest speed? Well, let's see. I'm going to do the ratio of this. The reason why I'm doing the ratio is to see how far shifted that is. For example, this one is supposed to be here, and this one is supposed to be here. So there is a huge shift in here for this one, so I know this one is faster than the other one. So that's basically what I'm trying to get into. So let's do f over f naught. Or do f naught over f, it doesn't matter. Because then we're going to see if I do f naught, because they are all, it's supposed to be f naught, but it's less, so I'm going to do this ratio in this direction. Had they been in the opposite direction, I would do the f over f naught to find them coming towards us. But this one, they are all receding. All frequencies are in the opposite direction. So 9.2 divided by 7.1. Let me get that number quickly. 9.2 divided by 7.1. That's roughly about 1.3. Okay. 8.6 divided by 4. That's roughly about 1.6. So we know B is moving faster than A. Okay. 7.9 divided by 6.1. That's roughly 1.3. Actually, C and A are moving almost with the same speed away from us, except if I take more sig figs, C is 1.2951 and A is 1.2957. So actually this one is faster than C. Okay? Because there is more sig figs in here that I'm neglecting. In this number is higher actually, although both of them, at least according to this data, are very close from one another. Anyway, 8.9 divided by, and that's 1.019 or something. So it's 1.1. Okay, so the fastest moving from us is B. Okay. Is that moving toward or away from us? No, from the detector, it's away. Which source is moving at the lowest speed relative to your detector? That's D. Lowest. It's almost the same frequency as the other one, whereas this one is the fastest. Okay. They are all receding from us. This is basically how Mr. Hubble discovered that the universe is expanding. Okay. What is the speed? What is the speed? Oh, in this case, remember f is equal to the square root. They're all receding, so the frequencies are less. So it's going to be c minus u divided by c plus u. Remember, the formula usually has a plus or minus divided by a plus, minus or plus. But since they are moving, I'm going to take the lower value in here and the lower value in there, and this will give me times f naught. So if that's the case, I'm supposed to find the value of u now, how much they are moving away from us. How can we do that? If I do f naught over f, and from here square this number, okay, so this is, I'm going to call it the ratio in here instead of carrying it with me. So this is a ratio squared. It's going to be, remember, it's going to be f naught over f is going to be c plus u over c minus u. Okay, and from here let's divide by c everywhere. I don't like this c in here. I like the 1 in here. So u over c, which is beta, 1 plus beta, is equal to r squared times 1 minus beta. Okay, does this make sense to me? So if I move this to the other side, it's going to be 1 plus r squared times beta, and okay, good. And I move the 1 to the other side, it's r squared minus 1. So everything is all well, so beta must be equal to r squared minus 1 over r squared plus 1. Okay, good. So let's plug in the slowest, because I want to know the speed of the slowest. So we know r squared is 1.1, so 1.1 squared minus 1 over 1.1 squared plus 1. Then this number better be less than 1, because if it's greater than 1, then we have a galaxy that's moving faster than the speed of light, and that's a problem. So we have 1.1 squared minus 1, that's going to be less than 1, of course, divided by 1.1 squared plus 1. 0.095 or 9.5%. So that's how much beta is. So it's a very small quantity. As a matter of fact, we could probably have used classical mechanics for this one because the speed is so small. Okay, it's less than 10% of the speed of light. So okay. Is that source moving toward or away? So they are all moving away. So for source B, what frequency would your detector measure if the source were moving at the same speed relative to the detector but toward it rather than away from it? Okay. Okay, I think this gave you a solution to one of the questions earlier because it was asking you whether or not they're moving away or not, and now they're telling you that B, had it been moving towards us, how much its speed, so we know then it was moving away from us. So this gave you a little bit of a help in here in solving this problem. So first of all, we need to find the frequency. We need to find the speed. Once we find the speed, we use the same formula for the Doppler effect, except that the frequency is shifted backward. So we're going to use the same formula for B now. So this was for D, by the way. For B, for object B, we use the beta is equal to r squared. Again, r squared is 1.6 squared minus 1 over 1.6 squared plus 1, and this should be higher than 9.5% because this has a higher shift. Okay, so let's see here. So again, I'll probably use the same formula in here. Oh man, I used it 2 times. Okay, and change this from 1.1 to 1.6. Go in the numerator and do the same thing. Okay, 0.438 or 43.8 or 44% the speed of light. Okay, well, I guess we probably need the correct number in here. 43.8 big percent, or 0.438. That's to be more exact. Obviously, it's much bigger than the 9.5%, and that's exactly what we wanted to know. Okay, we have found what beta is, basically. So we're going to come back to this expression and find what the frequency is. It has to be higher than the 8.6 if it's we're going to be moving towards us. So the frequency now, if the galaxy B, I'm going to call them galaxy because that's most likely what they are, is equal to the square root of 1 plus beta over 1 minus beta. I already divided by c in this expression in here. It's c plus u over c minus u and divide by c and everything because I already have beta times f naught. I know what this value is, so it's 1.438 divided by, what is 1 minus 0.438? That's going to be 0.56 or point something, okay? 1 minus 0.438 divided by the frequency, and the frequency is 8.6 terahertz. THZ. Okay, so what is that number gonna look like? So square root of, open parentheses, 1.438 divided by, the reason why I'm tipping a little bit of sig figs, I don't want surprises, because sometimes surprises will arise when you do rounding in here, especially in this case when you're dealing with the Doppler effect. I mean, the Doppler effect, it cannot be used, for example, to determine how fast the Earth is moving. Okay, so this number now, I have to multiply it by 8.6. That's 13.76 terahertz. 13.76, or roughly about 13.8 terahertz. Okay, as expected, the frequency will be higher if the galaxy is moving towards us. Okay, so that's question 66. Question 68, problem 68. And we're done. I know this recording is a little bit long, but believe it or not, I did this recording earlier in the day, but somehow I did not save it because it crashed on me at the end after I was done. Anyway, so what we have for problem 68, many of the stars in the sky are actually binary stars in which 2 stars orbit about their common center of mass. If the orbital speeds of these stars are high enough, the motion of the stars can be detected by the Doppler effect. So basically, let me draw what this thing looks like. So we have 2 stars, part of a binary system. they're orbiting their center of mass, and one of them, let's say for example at some point, is moving away, the other one is moving towards us. Both of stars are supposed to have the same mass, okay? And we were supposed to find, and we're looking at it from here. And what we do in here, look at the numbers in here. That's why I was telling you earlier about the Doppler effect. So the light that they are supposed to see in the laboratory, when we tested it, we found it to be 4.56811 times 10 to the power 14 hertz. And you're wondering why in the world we have so many sig figs in this problem. We have 1, 2, 3, 4, 5, 6, 7. Because when it comes to stellar motion, and like I said before, we cannot use the Doppler effect. If we try to use it, we're not going to detect much shift in the frequency, for example, of the sun, because the sun, as it spins around its axis, as it goes back and forth, first of all, it's not spinning fast enough for the Doppler effect to detect that motion. At least devices that we have are not precise enough to detect it. So here is a binary system that we look at it, and now we know what the frequency is supposed to be. But sometimes it goes higher and sometimes it goes lower. So sometimes we have a frequency, so this is F0, but F1 sometimes is equal to, that's a lower frequency, it's 4.56, again, 7710 times 10 to the power 14 hertz. You see, we have it shifted lower than the natural frequency, and sometimes actually higher than that natural frequency. And F2 is equal to now 4.56. So when the star is coming towards us, we're going to see this higher frequency. When it's moving away from us, we're going to see the lower frequency, 4.5689110 times 10 to the power 14 hertz. This thing has 7 sig figs. Okay, because now you want to find stuff in here that is extremely sensitive, so you need to have really equipment that is sensitive enough to these things. Determine whether the binary star system as a whole is moving away from us or towards us. Here is the problem. You have a system in here. You have the center of mass that is moving with its own velocity, v center of mass. Relative to it, there is an orbital motion that this stars are engaged with. Sometimes they're towards us and sometimes they're away from us. So when the star is away from us, its velocity is given, or the frequency is given, by F0 times the square root of C minus, okay, it's moving away from us. So in this case, I'm going to take a value for VCM in this case, and then say it's the velocity of the center of mass plus this velocity divided by C plus velocity of the center of mass plus V. So now I'm getting the relative velocity. This is the relative velocity with respect to the center of mass, and this is the whole velocity with respect to our frame. Now for F2, I'm going to do the same analysis with the exception that it's going to be C plus the velocity of the center of mass plus V over C minus the velocity of the center of mass plus V. From here, we're going to solve these equations. Basically, I have two equations, 1 and 2, and they have two unknowns. V, the relative velocity, which is this orbital velocity, and the velocity of the center of mass. Those are the two unknowns. Solve for the velocity of the center of mass. Make an assumption. Let's say, for example, it's moving away from us, okay, and draw it in this diagram. And if that's the case, then we should find a value for it. Sorry, this is probably okay, so I think I need to correct it in here. Okay, let me think. So if this is moving away from us, so this is correct. So the first equation is correct. If it's moving, this one is moving towards us, so this is V minus V center of mass. And this is V minus V center of mass. Okay? You do this assumption. If VCM turn out to be in the same direction as V, and it's positive, then it's moving away from us. If not, it's moving towards us. So we have two equations with two unknowns. We have F2, we have F1, we have F0. Okay? We should be able to solve these two equations and find these velocities. Okay? the speeds involved are much less than c. So technically, if they are much less than c, so we probably are going to use non-relativistic Doppler effect. Okay, we're going to use non-relativistic Doppler effect and solve the problem. So delta f over f is just u over c, with the exception that u now is relative velocity plus the orbital velocity plus the velocity of the center of mass. Okay. Now they tell you the light from each star in the binary system varies from its maximum frequency to its minimum frequency in about 11 days. So we know in 11 days this is max, and then it's going to come back in here. So we know the period of revolution it's 11 days. Now this stuff from here on is nothing to do with the chapter. This stuff is from physics 1, actually, when you guys were doing orbital mechanics, when you're doing not orbital, yeah, classical mechanics. It has orbital mechanics in it. Determine the orbital radius r and the mass m of each star. Okay, here's the thing. What we're going to say in here is this is a circular motion. So if I apply f equals to ma to it, and that's because, again, they are making the assumption that these velocities are a lot less, so we can do f equals to ma in here, so we're in classical mechanics. So what we can say in here is that the mass times the acceleration, so this is the radius r, the mass times acceleration in here. So first of all, we have v, we have t, so technically we should be able to get, since we found v from the previous question, we have t, so we can just do v equal to 2 pi omega times r, or 2 pi omega r, and omega is equal to what? 2 pi divided by t times r. Okay, so this is an expression, or 2 pi r divided by. So from here you find the r, the radius of this orbital motion. Okay, because t was given 11 days. This is what you observed. V you calculated from previous question based on the Doppler effect. Once you have that, you have the value of r. So now you know r. Okay, since we know r, we can do f equals to ma, and f in this case is the force due to Mr. Newton, which is g times the mass of the first times the mass of the second, which is the same mass, divided by the distance squared, and the distance squared is 2r squared, must be equal to force times acceleration, and the acceleration in this case is v squared over r. Cancel the mass, and from here you should be able to find what the mass is, okay, of each star. R, you calculated it. V, you have it. You calculated it from the Doppler effect. R, you calculated it from this basically equation that you guys have seen, which is just the circumference divided by the period. The circumference is 2 pi r divided by the period, because it takes a whole cycle to go once, okay, around that circle. And now you have the answer to basically the mass. And they want this mass to be expressed in terms of the mass of the Earth. So the expression, so first of all, let me cancel one of the r's in here. So what do we have in this expression? We have m equals to v squared, that you get from the Doppler effect, times 4, 2 squared is 4. You have one of the r's survives in here, divided by g in this case, okay? And r, you get it from this expression. You have everything in this problem. V, you get it from the Doppler effect, so you have the mass. They wanted to use it in the mass of the sun. Is the symbol of the sun? I forgot what it is. I think it's the dot in here, which is given to be 1.99 times 10 to the power 30. Roughly, it's 2 times 10 to the power 30 kilograms. So basically, all you have to do is just divide that number by it, and that's it. At some point, they want to know and also compare r to the r. Once you find it, compare it to the distance between the Earth and the Sun, which is 150 million kilometers, or 150 times 10 to the power 8 meters. Okay, so whatever you find in there, divided by that number to see how much astronomical units that is, because that's what an AU is. Okay, so I hope you guys finished these problems. I know it's been it's an hour again. If you have any questions about them, please let me know, okay? So you have all of these problems, and there are quite a few of them, 1, 2, 3, 4, 5, 6 problems from this chapter, and you should be ready for exam. This is exam 2, okay? It has nothing to do with this exam, but you should be ready for this exam too. Thank you.